Welcome, everyone. Today, we're diving into the fascinating world of P versus NP and exploring what it means for discovery and existence in mathematics. Every time you see a beautiful math result, there are really two stories. Someone struggled to discover a proof, and later many people simply checked that proof. Today, we ask how different those two stories really are, empowered by looking at a question called P versus NP. The core idea will start from something familiar, that checking a solution feels easier than finding one, and we will gently connect that feeling to the classes P and NP without any coding. Our path is simple. First, we unpack what NP really means in terms of existence. Then we see proofs as certificates. Then we compare search with verification. And finally, we step back to ask what this says about the nature of mathematics.
So by the end, I should see P versus NP, less as a coding puzzle and more as a question about how math itself works?
Exactly, we will treat it as a question about whether mathematical existence automatically gives us a practical way to discover what exists. First, notice the easy side of math work. Once a proof is written down, you can go line by line and see whether each step is justified.
Yeah, that feels like grading homework. It can be long, but it is pretty straightforward.
In contrast, discovering a proof starts with a blank page and no clear path, and you have to guess, explore, and backtrack.
That is the part that feels creative, like solving a puzzle nobody has solved before.
Most of us feel there is a big difficulty gap here, that inventing arguments is much harder than checking them once they exist. The class P versus the class NP asks whether, in a precise sense, fast checking is actually just as powerful as fast discovering.
So the puzzle is whether that gut feeling that discovery is harder is actually baked into mathematics or might be an illusion.
Next, we will make this more precise by explaining what NP really means in terms of existence with a short witness. Let us strip away the jargon and talk about what NP really captures. Think of it as a giant family of questions where a yes answer always comes with a short, checkable piece of evidence.
So NP is less about computers and more about the idea that witnesses for existence are not too huge.
The first bullet says that for every yes instance of the problem, there is some compact witness, some object you could write down without filling a library. A witness or certificate is just that evidence, like a completed Sudoku grid that proves the puzzle is solvable.
Right, once you show me the filled grid, I do not need to be clever anymore, I only need to check.
And P insists that there is a verifier, a systematic way to take a proposed witness and check in a reasonable amount of time whether it really works. From a mathematician's point of view, NP is the world of existence statements that come with short, checkable certificates of truth.
So when I say there exists something with some property, I am really hoping it lives in this NP-style world where a short witness could prove it to me.
Next, we will connect this idea of short witnesses directly to the central object of mathematics proofs themselves. Now let us bring this back to something every mathematician cares about deeply: proofs.
You are going to argue that proofs are basically those witnesses we just talked about, right?
Exactly, a proof is the classical mathematical certificate that some statement is true. First, a proof is finite. It is some sequence of symbols on a page, not an endless cloud of intuition in someone's head. Second, checking a proof can be reduced to very local questions, like whether each line follows from earlier ones, which makes it almost mechanical.
So a computer could in principle act like the strict grader that checks each inference rule.
When a proof is reasonably short, it looks exactly like an NP witness, a compact object that some verifier can check efficiently. The mystery is whether we can always or usually find those short proofs efficiently when they exist, or whether searching for them is fundamentally harder.
If P equaled NP, that would mean that as soon as a short proof exists in principle, some smart but systematic method could always dig it up quickly.
To feel the gap more vividly, let us contrast the experience of checking a candidate solution with the experience of searching the whole space for one. Here is a concrete way to see the difference between searching and verifying. Think of verification as driving down a straight highway and search as wandering through a huge maze of possibilities. On the screen, you'll see a simple equation about three integers like the ones behind Pythagorean triples. If someone hands you specific numbers for x, y, and z, verifying is easy. You compute both sides and see whether they agree.
That is just arithmetic. There is no big idea needed once the candidate is in front of you.
But if nobody gives you a candidate, you might have to search through many triples of integers with almost no guidance about where the good ones live. This is where the picture helps. Verification is like driving a clear road someone already paved, while search is like exploring a branching maze without a map.
I can see that in a maze you might pass the right door and never notice, whereas on a highway the path is fixed.
The P versus NP question asks whether for all these maze-like search problems with short witnesses, there is actually a clever way to drive a highway straight to a solution.
And most people believe there are mazes that cannot be flattened into highways, but we have no proof either way.
So the suspected gap between highways and mazes shows up even in basic existence questions, and now we can ask what that gap means for the structure of mathematics. Mathematicians already know there are limits to proof through Gödel's incompleteness theorems. P versus N. P asks about a different kind of limit, not whether proofs exist at all, but whether they are findable in a reasonable way.
So this is about the limits of what we can do with realistic effort, not the absolute limits of logic.
Gödel showed that in any rich enough formal system, there are true statements you can never prove within that system. By contrast, P versus NP focuses on statements that do have short proofs but asks whether there is always a practical method to uncover those proofs. It asks whether there is a structural gap between what is provable in principle and what is provable with only a reasonable amount of time and effort.
So even if a proof fits on a page, it might still be effectively invisible if no efficient search can find it.
This makes P versus NP a structural question about the architecture of mathematical truth, not a technical footnote in computer science. Let us now step back and collect the main ideas we have built about existence discovery and why mathematicians care so much about this problem. Before we finish, let us summarize what we have learned about P versus NP from a mathematician's point of view. First, NP is the realm of problems where every yes answer comes with a short witness that a verifier can check quickly. Second, mathematical proofs are exactly these kinds of certificates, short objects that convince us something exists or is true.
So NP is like the universe of theorems with short proofs seen from the outside by a verifier.
If P equaled NP, then whenever a short proof or witness existed, there would be an efficient method to discover it, making discovery as easy as checking. Most experts believe P is not equal to NP, meaning there is a genuine structural gap between existence with a short proof and our ability to feasibly find that proof.
So the real question is whether mathematical creativity is something fundamentally beyond fast verification or just a super smart version of it we have not discovered yet.
In the companion talk, we will see how the same question about existence and discovery shows up all over computer science and the real world. Let us close with a quick check on understanding and a moment of reflection. First, think about the statement that a particular Sudoku puzzle has a solution and ask whether that is more like a P problem or an NP problem. It is NP type. Because if the answer is yes, a short witness exists, namely a filled-in grid, and checking that grid is fast, but finding it seems much harder.
So the certificate is the completed puzzle and the verifier just scans rows, columns, and boxes to see that everything fits.
Now pause and imagine a world where P equals NP, where any short proof could be found efficiently. What would that do to the idea of mathematical creativity?
It feels like a lot of the mystery of proofs would turn into engineering designing the right search instead of flashes of human insight.
In the next part, we will see how the same gap between existence and discovery explains why P versus NP appears in scheduling, optimization, and even digital security. If you keep the lens of existence versus discovery in mind, you will be ready to see P versus NP everywhere mathematics meets computation.
Thanks for watching this. Subscribe to Thinking in Math for more topics. We welcome your feedback, leave questions and suggestions in the comments.